In this lesson, we're going to look at a third application of de Moivre's theorem. You've already seen a couple of very useful applications which we consolidated in the last lesson. This third application is using it to find sums of some real series, and they're sums that they're types of series that we haven't really come across before, and you don't actually know with all of the techniques that you already have to do with series how to sum series that look like these. So what we're going to remind ourselves of first is looking at sequences and series. So if we were in the classroom, I would ask you as my first question, what's the difference between a sequence and a series? Often people don't know because they're taught together and the words are quite often used side by side. But basically the difference between a sequence and a sequence is a list of numbers that follow a certain rule. So let me give you a sequence. Okay, something like that. So that would be a sequence of numbers. Now the corresponding series would be basically taking those numbers and adding them together. Okay, so you've come across a few types of series or sequences in GCSE, arithmetic and geometric. So let's just remind ourselves what the difference are between the two of those. This one that I've drawn up here is an arithmetic sequence. Reason being, what we do to get from one term to the next is we add a constant difference each time. So you can see with this, we're adding 3 each time, okay, to get the next term. Now there is a formula that was in the formula book for finding the sum of the first n terms from an arithmetic series. You may remember we've come across this before. We used it when we were doing the summing series chapter, and we used it to sum r equals 1 to n of r, because remember we said the formula for that is n over 2n plus 1, and where we got that from was we got that from using this with the arithmetic series, okay, being the natural numbers. So a is your first term and that's 1, and l is your last term, which is n. Okay, so we've used that one already. There's also geometric sequence or series, and the thing is with those that rather than adding a constant difference to get the next term, what you do is multiply by a constant ratio to get the next term. So let me give you an example: 2, 4, 8, 16, 32. So I've multiplied by 2 each time. Now there are equivalent formula in the formula book that you probably haven't used before, but you will use later on in year 13. And that's for summing geometric series. Now there's 2 formulae, and we're going to be making use of both of these in the work we're going to be doing in this lesson. Okay, so there's a sum to the first n terms. Remember, r is the constant ratio, so that's the thing you multiply by each time to get the next term, and a is your first term. Now, as well as having a sum to the first n terms, there's also a sum to infinity. So I'll just take a moment to talk to you what that's all about. The requirement to have a sum to infinity is that the ratio is less than 1. Now let me give you an example of a sequence or series with ratio less than 1. So if I start with 1, if its ratio was a half, then it would go 1/2, quarter, eighth, 16th, etc. Okay, so you can see what's happening there is that the terms are getting smaller and smaller and smaller. So if I was summing the series and adding them all together, when I've got quite a way down the series, remember the series is infinite, when I've got quite a way down it, my terms become so small that they become insignificant. So in that situation, I can actually get an expression for the sum to infinity, because this assumes that after a certain number of terms, my terms become negligible. So if I was to do the sum to infinity of this particular series here that I'm adding together, a is the first term, r is the ratio, which is a half, okay, so I end up with 1/half, so I end up with 2. So if I was to sum all of these together, the sum to infinity would be 2. So we're going to make use of these 2 because the series we're going to be looking at, okay, are going to end up with a little bit of work, a little bit of use of de Moivre's theorem. They're going to end up as geometric series. Okay. Let's have a look at the types of series we're going to be looking at. We're going to be looking at series like this, okay, and how we can sum them is by making use of complex numbers. Now, first thing to say is if you look at that, that is not a geometric series and that is not our arithmetic series. I am not adding a constant difference to get the next term, or I'm not multiplying by a constant ratio to get the next term. But if I make use of complex numbers and de Moivre's theorem, then I can convert it to a type of series that I can sum. So let's just have a look at how we go about doing that. Okay. So here's just a little bit of sort of background information on it really. So let's have a look first of all at this series here. Now the series goes e to the I theta, 2 plus 2 e to the 2i theta, e to the 3i theta. So if I asked you what type of series that was, it's a geometric series because to get from one term to the next, I multiply by e to the I theta. My first term also happens to be e to the I theta, so this is my r, remember, in my formula, and my first term is e to the I theta. Okay, now this series here, it's a finite series, so it's the first n terms. Okay, so I can find an expression for the sum for the first n terms using my formula. Here's my formula, a times r to the n minus 1 over r minus 1. Okay, doesn't matter which way round these are, it's also equivalent to do 1 minus r to the n over 1 minus r, which may well be quoted in the formula book. Okay, these are on page 5 in the formula book, I should have mentioned that, so do go and look and find them because you'll be making use of them. Okay, so that would be my sum of my series. Now here's the really clever part. Okay, if I take my initial series and I split it, because we know e to the I theta is cos theta plus I sine theta. So if I split each of the e terms in the series, then I get that. If I group them, and I group all of the real bits together and I group all of the imaginary bits together, then you can see I get something that looks very similar to the previous series that I was looking at that had causes or sines in. I think the first one we looked at had sines in it. So what that tells us then is if we can basically sum this series here and get this expression, then if I want to sum something that looks like the cos bits, I can find that sum. And can you see from this line up here that the cos bits is the real bits of that sum and the sine bits are the imaginary bits of that sum. So if I can form this expression and then with a bit of manipulation, you'll see we need to be able to work out which is the real bit and which is the imaginary bit. If I can work out which is the real and which is the imaginary bit, then that equates to my cos bits or to my sine bits. So that's basically what we're going to be doing. Now, I think it always becomes a lot clearer through some examples, all right? So we've got a couple of examples that we're going to have a look at. So here's example number 1. So pause the video and just take a moment to write that down nice and carefully. Okay, now you often get in questions that are set on these, you often get a part I, and the part I is usually proving some sort of identity that we can then go on and use in the second part. All right, so proving that is not usually very difficult, but always once you've proved it, keep an eye out in the second part how you can make use of it. Okay, so let's prove that. So I'm going to start with the left hand side because the left hand side has got 2 brackets which naturally you would think, well, let's multiply out those brackets. So I get 4 plus 2e to the I theta plus 2e to the minus I theta, and then these 2 times together give us 1, okay, because you're going to add the indices, so you get e to the 0, which is 1. Now let's have a look at what we get here. 4 plus 1 gives me 5. Now what have I got? I've got 2 lots of. I've got e to the I theta plus e to the minus I theta. Now I can convert that to the cos plus I sine form, so I get cos theta plus I sine theta plus cos minus theta plus I sine minus theta. So I'm showing nice and clearly where this is coming from because I have been given the answer. And then here's the bit that you are used to using quite a lot. Cos plus I sine stays like that. Remember, when you've got minus the argument, the cos bit is still cos theta, but the sine bit becomes minus I sine theta. Okay, and that is going to give me the bit that I want, 5 plus, well, you end up with 2, and you end up with 2 lots of cos theta. Okay, so I'll just put it in a couple of steps to show really nice and clearly where it comes from. Okay, so that's the first part of the question done, and we're going to make use of that in the second part of the question. Now, for the second part of the question, the examiner has told us to consider C minus IS. If you're not told to consider C minus IS, then by default you normally would consider C plus IS. Okay, we'll see why in a minute, why they've said C minus IS, but let's write out what C minus IS is. Okay, we've got S here and we've got C here. Okay, so C minus IS equals, right, the C bit goes 1 minus cos theta over 2 plus cos 2 theta over 2 squared, and then dot, dot, dot. Right, here's a bit to notice when you're doing these questions. If you get a dot, dot, dot at the end here, that means this is an infinite series. So you are doing sum to infinity. You'll see in a moment we do a question where we've got an end term as well. If that's the case, you're using the sum to the first n terms. Okay, so do look out for that. We'll use that in a minute. Right, so C minus I times S, and S is sine theta over 2 minus sine 2 theta over 2 squared, dot, dot, dot. I'm not going to write them all out. Now, here's what we do. We group together the cos and the sine bits that have the same argument. So I've got minus, I've got half outside, and I've got cos theta plus I sine theta, because I've taken the minus a half outside. What have I got here? Plus 1 over 2 squared cos 2 theta, okay, plus I sine 2 theta, okay, and I would get, then I'd get minus 1 over 2 cubed, etc, etc, etc. So let's write this then in our exponential form. I get 1 minus a half, that's e to the I theta. I get plus 1 over 2 squared, that's e to the 2I theta. And my next one, 1 over 2 cubed, e to the 3I theta, and it would go dot, dot, dot on. So this is a geometric series. Okay, so this is a geometric series. So geometric series. Now I'm going to use my formula in a minute, my sum to infinity. So let's state what A is. Remember, A is the first term, so that's 1. Let's state what my R is. R is what I multiply the first term to get the second term, minus 1/2 e to the I theta. Okay, so for this particular question, I am going to be doing a sum to infinity. Okay, because of that dot, dot, dot at the end of the question. Sum to infinity, A over 1 minus R. So let's pop in my bits here. A is 1, R is, so that's going to become plus 1/2 e to the I theta. I don't particularly like having fractions within fractions, so I'll multiply top and bottom by 2, and I get 2 over 2 plus e to the I theta. Now, the question has asked me, here's the show that. The question has asked me to show that S equals this. Now, S is minus the imaginary bit of the thing I've summed. So I need to be able to find out from this term here, I need to be able to find out what is the real bit and what is the imaginary bit. Okay, so here's where we make use of what we did in part I. You can see the denominator of the thing I'm trying to show is 5 plus 4 cos theta. How do I get 5 plus 4 cos theta? Look at what we did in part I. I get that on my denominator by timesing it by 2 plus e to the minus I theta. Now I don't want to change the expression, so I must times the top by the same thing. If the question doesn't have a part I like this, then the rule is that you always times top and bottom by whatever the denominator is, but the argument of e, you make it minus what it was. And you'll see why that's useful in a minute. Okay, so let's times that out then. So on the top, I've got 4 plus 2e to the minus I theta. The bottom, I can simply go straight to saying that's 5 plus 4 cos theta because, okay, this bit here is from part I. So I can go straight to that. That's absolutely fine. Now, I want to pick out minus the imaginary bit because remember, minus the imaginary bit is my S bit. How do I split it into real and imaginary bits? Well, what I do is I split the e to the minus I theta into cos theta minus I sine theta. Hopefully you're happy with me going straight to that. Okay. So now S is minus the imaginary part of so it's minus the imaginary part of my C minus IS. Okay, I've just lost my pen for a minute. There we go. Sorry, that disappeared. Minus the imaginary part of my C minus IS. Let's have a look at my expression. Let's find the bits that have i's in them. It's this bit here. It's got a 2 out the front as well. Okay, so minus the imaginary bit is going to give us 2 sine theta. Remember, when you're picking the imaginary bit, you don't write I, over 5 plus 4 cos theta, which is the answer that I wanted. If it did ask me for what C was, okay, it hasn't, but just as a little aside, if it did ask me for what C is the real part of my C minus IS. So let's pick that out. That's going to be 4 plus 2 cos theta over 5 plus 4 cos theta. So I get the C and the S for free by doing that. These are quite complicated questions, okay, but if you work your way through it, if there's a part I to it, make use of the part I to help you. If there isn't, then consider C plus IS and make yourself one of these geometric series, okay, in terms of e to the I thetas. That's the way to go forward with these. Right, on to example number 2 then, okay. If you have a look at the question, all right, S is a series. Can you see the series has a final term here? So this is not a sum to infinity. This is a sum to the first n terms. Okay, so S is geometric. Now, to use my formula for summing geometric series, I need to know what A is. A is my first term, e to the I theta. R is the ratio. What have I multiplied to get from this to this? Another e to the I theta. And remember, n is how many terms have I got? If you count them all, I've got 8. Okay, so S is going to be equal to the sum of the first 8 terms. All right, now here's my formula. It is A times r to the n minus 1 over r minus 1. So let's pop in the bits we know then. E to the I theta times e to the I 8 theta, because n is 8, minus 1 over e to the I theta minus 1. Now that is my answer, but have a look at what we're trying to show. We're trying to show that what I've got is equivalent to this. So we're going to have to do a little bit of work to show that that's equivalent. Okay. Now we know that e to the I theta is equal to cos theta plus I sine theta. Okay. So I want to make this bit on the denominator, I want to make that become sine theta over 2. So I don't want to have thetas here, I want to have theta over 2's here. Okay, happy with that? So if I take out a factor of e to the I theta over 2, okay, if I take that out top and bottom, then I can cancel those, all right? And you'll see in a minute why that's useful. The denominator becomes e to the I theta minus 2 minus e to the minus I theta over 2. And I've made it like that because I want sine theta over 2. I don't want sine theta, I want sine theta over 2. Okay. Now, what have I got on the top then? I've taken out that as a factor because I want to be able to cancel these. Okay, so I end up with e to the I theta over 2 times e to the I 8 theta minus 1. Okay, now let's have a look at this bit on the bottom then. This e to the I theta over 2 minus e to the minus I theta over 2. Okay, let's have a look at that. Now I'm just going to write it up at the top here. E to the I theta over 2 cos theta over 2 plus I sine theta over 2. Okay, so what we're doing is we're doing this little bracket here. I just put a little star by it and I put a little star up here. So that is my e to the I theta over 2 minus this is cos minus theta over 2, which is the same as cos theta over 2, and a minus in the middle, I sine theta over 2, because remember when you have minus the argument, okay, you get this minus sign in the middle. So the cos's cancel out and I end up with 2I sine theta over 2, which is giving me along the right lines of what I want on the denominator. Okay. So the denominator becomes 2I sine theta over 2 from what I've written at the top. Now I'm going to do the same to make the numerator what I want in my show that. So you can see that I want sine 4 thetas. You can also see that I want an e to the 9I theta over 2. So what I'm going to do is I'm going to take out from this bracket, take out a factor of e to the I 4 theta, because taking that out is going to give me e to the 9I theta over 2, and inside my bracket it's going to give me e to the I 4 theta minus e to the minus I 4 theta. Okay, and just to say, the reason I'm doing it is because I'm looking at my show that up here, I'm looking at it and I'm trying to make my expression look like that. Okay, now the numerator, okay, that in the same way as what I did up here, hopefully you can see that this gives me 2I sine 4 theta. It's exactly the same as the thing I did on the top, but instead of having a theta over 2 as an argument, I've got a 4 theta as an argument. So you can see the 2 i's then cancel and I get exactly what I want. Okay. So, tricky question, that one, because you had to kind of use what you're trying to show, you had to use that to guide you with what to do with the expression that you ended up with once you'd used the summation formula. All right, but hopefully you've seen, replay this if you're not sure, hopefully you've seen how I've been guided by trying to make it look like the show that I've been given. And they would have to give you that because you can write this expression in a lot of different ways. Okay, right, let's go on to the part 2. Part 2 is actually a lot easier than part 1. Okay, so for your part 2, we've now defined P and Q. Okay, so if we look at S, we're kind of doing what we were doing in the previous question, a little bit in reverse. If you look at S, well, S is my e to the I theta, e to the 2I theta, etc., etc. So if I write that as my cos plus I sine, it's cos theta plus I sine theta plus cos 2 theta plus I sine 2 theta, all the way, dot, 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 all the way up to cos 8 theta plus I sine 8 theta. So if I have a look at that compared to my P and my Q, it's P plus IQ. So what that tells me is, if I want to get an expression for P, P is equal to the real part of S. Okay, now up here, sine 4 theta is just a number. Okay, and sine theta over 2 is just a number. All right. The thing that I can split is my e to the 9I theta over 2. I can write that as cos 9 theta over 2 plus I sine 9 theta over 2. Okay, and then I've got my sine 4 theta on the top and my sine theta over 2 on the bottom. So if I'm picking out what the real part is the part that doesn't have an I. So the real part is going to be cos 9 theta over 2 times sine 4 theta over sine theta over 2. And we all know from our reciprocal trig functions that that is equal to cos 9 theta over 2 sine 4 theta. 1 over sine is cosec theta over 2. Okay, in a similar way then, they want the expression for Q. Q is the imaginary part of S, because it's P plus IQ. So the imaginary part is going to be sine 9 theta over 2, sine 4 theta, cosec theta over 2. All right, and the last bit, Q over P. If we look at Q over P, this is quite interesting. If I do that divided by that, okay, the sine 4 thetas cancel, the cosec theta over 2's cancel. So I simply end up with sine 9 theta over 2 over cos 9 theta over 2. And what does that equal? Tan 9 theta over 2. How clever is that? Okay, so slightly different question. That one shows you that it is a sum to a certain number of terms, whereas the previous one we did was a sum to infinity. So for a sum for a certain number of terms, we're using that other formula. And then we've split it as your P plus IQ in this example, okay, and then made use of that. Right, one last example. Now the reason I'm doing this last example is it's slightly different to the other two. You can see it looks different because it's got these things in it, okay. Looks similar because it's summing series that have got coses and cos 2 thetas and sine 2 thetas. This is the different bit. You will have seen this before when you've done your binomial expansions. This is the same as n choose 3. Okay, this is how they write them in the formula book. Okay, so can you see nowhere in the question does it say consider C plus IS? So this particular example, you have got to know that when you get series like this, you consider C plus IS. And that's what I affectionately call these types of questions, C plus IS questions. So if I look at C plus IS then, I've got 1 plus n choose 1 cos theta plus n choose 2 cos 2 theta, dot dot dot, all up to n choose n cos n theta. So notice this isn't a sum to infinity, this is a sum to n terms, plus I times n choose 1 sine theta, n choose 2 sine 2 theta, plus all the way up to the last one, n choose n sine n theta. Okay, now as we did before, I'm going to group the cos plus I sine bits together. I've got my 1 at the beginning, so I'll just leave that there. I've got here n choose 1 cos theta plus I sine theta, so I'm going to write that as e to the I theta. I've got n choose 2 cos 2 theta plus I sine 2 theta, so that's e to the 2I theta. And I'm going to do that all the way up to my n choose n. I've got cos n theta plus I sine n theta, that's e to the I n theta. Now, normally we would look at that and say it's a geometric series. Okay, this one isn't though, because of these n choose 1, n choose 2, n choose 3 bits. But it is something that you have come across before. So again, if we were in the classroom, there'd be a chocolate prize for anybody that can come up with this. Okay, have a look at that. That is the same as 1 plus e to the I theta to the power n expanded binomially. So you just convince yourself that that's the case. You get the 1 at the beginning, you get the n choose 1, one of those, you get the n choose 2, two of those, etc., etc. How clever is that? Okay, so now what we need to do is, I'll show that. So we now need to, okay, be able to show that C, which is the real part of this, that C is equal to this. Do you notice again, we've got theta over 2's in it. So because of that, that tells me that I'm going to, inside my bracket, need to make it e to the I theta over 2 so that I get the cos theta over 2. So I'm going to take out a factor from my bracket of e to the I theta over 2. Okay, I'm going to do it within another bracket. So now I've taken out that factor, sorry, it's not 1 anymore, is it? Now I've taken out that factor, what do I end up with? E to the minus I theta over 2 plus e to the I theta over 2. Okay, yeah, all raised to the power n. All right, so what I end up with here, all right, is e to the I n theta over 2. Now let's sort out this bracket. Let's sort out this. We've done this before. You might remember what it is. If you don't, write it out. That first bit is cos theta over 2 minus I sine theta over 2, isn't it? Yeah, because it's got minus the angle. That second e to the I theta over 2 is cos theta over 2 plus I sine theta over 2. So in this particular example, that becomes 2 cos theta over 2. Okay, so what I end up with in here is 2 cos theta over 2, all raised to the power n. Okay, now is where I need to pick out the C bit. C, remember, is the real part of the C plus IS. Okay, to pick out the real part, I have to write my e to the I n theta over 2 as cos n theta over 2 plus I sine n theta over 2 times by, run out of room there, but it's that thing goes in that bracket there. Okay, so if I'm picking out the real bit is going to be this part times the bracket. So the real part is cos n theta over 2 times the bracket, which is 2 cos theta over 2 to the n. Right, part B is on about S as well. Well, S is the imaginary part of C plus IS. And the imaginary part is going to be the same thing, but with the sign here. So sine n theta over 2 times 2 cos theta over 2 to the n. Okay, final bit says show that S over C equals tan n theta over 2, S over C. Okay, so you can see that's your sine n theta over 2 divided by cos n theta over 2. Okay, because the brackets to the power n cancel, so that gives me my tan n theta over 2. So this last example, slightly different, okay, and this should prompt you to remember, if you see a question like this, it's still approaching it in the C plus IS way, but that C plus IS way is going to give you a binomial expansion here, okay, binomial, rather than a geometric series, which the other ones have before, okay. These are quite tricky. So what I've got for you to work your way through, there's not a lot of these questions in the book, so I've got a separate sheet for you to work through. What I'd like you to do is to take that sheet and give it a really, really good go. Okay, I have also posted within Teams, I have also posted work solutions to these for you to have a look at once you have given it a really good go. All right. And then when I next speak to you on Teams, I'll sort of go through it as well. But I do want you to not just copy the work solutions, I do want you to give these questions a good go. Things to look out for is it a sum to infinity, or is it a sum to the first n terms? And if there's parts A of the question, see how you can use those in subsequent parts of the question. Okay, right. Quite tricky, but good luck with those.